In the previous video I've shown you how to connect a standard SPDIF source to the front panel so that the output signal appears on the headphones jack. As I've said, I've completely reverse engineered the digital part of the front panel, so we're gonna take a look at the schematic that I've made. I am also going to show you some oscilloscope traces of SPDIF and I2S signals. So this video is going to be a bit more technical, but I hope that you will find it interesting. Okay, this is a overview schematic of the digital part that I drew as part of this reversing, sort of as a notes for myself. And as you can see, we've got the buffer here, 74F245. And yeah, the SPDIF signal we were talking about for the headphones comes in over here on the pin header, goes down through a resistor and comes out on the buffer here, and then it simply appears down here just to enter the first IC, the second IC and the front end. This is generally the area where we were probing the I2S signals, but there is just so little happening there that there wasn't any point in drawing these as actual wires, so this is just a sort of block schematic way of indicating how that works. There are two more things on the DAC. So we've got the mode pins, because this CS4392KZ DAC has a couple switchable modes. So you can see that the mode pin number 2 is pulled down to ground through R82, but the M3 pin is actually connected freely, and it is connected to a pin labeled on the schematic DAC M3 to a pin on the pin header, pin number 11 here. And what this signal does, it switches the headphone DAC mode between quad speed and single speed. So this is like an interesting tidbit if you are trying to make something more out of to push the headphones DAC a bit more. But as you can see, there are loads of other things on this board, so let's take a quick tour through the schematic. We've got a TOSLINK input over here, which is on the top mezzanine board. There's an indication it goes through a pin header down to the bottom board, and then enters a 74125 buffer. Now the buffer is driven by a signal which I've called TOSLINK in disable over here. The output from the buffer simply goes to SPDIF in, and that signal goes down to that actual output buffer, that 245 buffer, and then ends up on the pin header. But let's take a look at the TOSLINK in disable signal and the TOSLINK copper input. So this down here is the SPDIF input over an RCA jack, so this goes over copper. As you can see, it's got a 75 ohm termination here, and it's AC coupled into a general purpose differential power transceiver, the 75179B. And the output from the differential pair transceiver it forks over here, so one path goes into a similar buffer setup. So this goes to a 74125, and the output from that goes to the SPDIF in. But there is also this clever circuit down here, which is essentially a signal detector. So this circuit detects whether there is a SPDIF input connected. When there is a signal on the copper SPDIF line, the TOSLINK in disable signal goes high, and this buffer is enabled to connect the SPDIF input to the SPDIF in signal. And when there is no such signal over here, then this transistor stops conducting, and TOSLINK in disable goes down. This enable, which is a negated input, goes up. And as I said, the TOSLINK in disable signal goes down, so this buffer is enabled and the signal is switched so that the SPDIF in is connected to the TOSLINK input. So this is how they share both TOSLINK and SPDIF signals on one SPDIF stream. So the way this is set up means that if you have a TOSLINK signal and a SPDIF signal at the same time, the SPDIF signal generally takes precedence and disables the TOSLINK signal input. Now let's focus on the TOSLINK and SPDIF output, which is generally simpler. So again, this signal enters the pin header over here and then forks out through these two buffers. So this is the SPDIF output from the sound card. And as you can see, it splits over here too. One of the paths goes directly to the optical output. This is pretty simple. That's just a optical transmitter like a diode or something. And the other part goes through this these two inverters, which buffer the signal and increase the drive strength. Then goes through this filter over here and an isolation transformer to end up on the SPDIF output, which is the RCA jack on the front. And the last thing that's left are the two auxiliary inputs. So we've got aux1, which is the line in or mic in. It goes on the standard jack on the front. There's a gain potentiometer with a switch which switches between the mic mode and line in mode. So this is the front end over here. This is a single-ended signal, and the ADC is a UDA 1361, and this is an I2S ADC which has got I2S signal. In this case, the signals are called BCK, WS, Data O, and Sys CLK. So these three first are I2S. So this is the sample clock, this is the left and right clock, this is the data. And this system clock is just the clock for the ADC circuitry to do its job. As you can see, the I2S bus is shared between these two DACs because the auxiliary input 2 on the top board is also the same IC. So there's like a small front end and a 1361 ADC, and as you can see, the signals which come from the sound card, which is the two clocks and the system clocks, they are all shared, and you essentially get a separate data outputs from the DACs. Now all of these signals are also buffered by the buffer on the before going to the pin header on the back. So that's all when it comes to the deep dive into the hardware internals of this thing, the digital part at least. Overall, this is a pretty neat board. The schematic I was showing you, along with a simplified schematic and a bit of text, is going to be on my blog, so check the video description for that. The first signal in the headphone jack path is SPDIF. So this is how SPDIF looks like on an oscilloscope, and if you are not familiar with what coding scheme this is, so this basically looks like two square waves, right? A square wave with some frequency and then seemingly at random interleaved a square wave with another frequency, which is twice the frequency of the first square wave. And this is so-called Manchester coding. Manchester coding is a coding scheme in which instead of encoding 1 and 0 as a high and low logic level respectively, you encode 1 as a transition and 0 as no transition. So if we zoom in and stop the acquisition on the scope, then you can see Then you can see over here that we've got a 0, a 0, a 0, a 0, and then we've got a 1 over here because there is an extra transition. Then another 1 here, then a bunch of zeros and 2 1s over here, then a 0, and then a bunch of 1s back there. So as I said, this is called Manchester coding, and this coding scheme has got a couple of advantages. The first one is that it's a self-clocking coding scheme, so with a clever electronic circuit you can extract the base bit clock from this. So yeah, in case of zeros, this is just your bit clock, and then you synchronize to this bit clock, and when you're looking for a 1, you're just searching for that extra transition. So this is a self-clocking scheme. Thanks to that, you only need to carry 1 signal instead of 2 signals, and you don't have clock skew because the clock is encoded in the actual data signal itself. Another one is that because there is always a guaranteed transition, the DC content of a Manchester encoded signal is 0. And as you can see, I've got my probe scope DC coupled, and the actual ground level is over here because on the sound card the SPDIF output is actually capacitively coupled. And this is another advantage of of Manchester coding, is that because the DC component is 0, you can easily couple it through AC coupling devices, like for example capacitors or isolation transformers. So right now I'm playing some music through the sound card, and you can see that there is a repetitive pattern in this signal. So the paths that stay the same over here would be the synchronization bits, and the paths that change are the data bits, because obviously every sample has a different value. Now if I pause the music, so now I'm transmitting digital silence, which is almost always zeros. You can easily see where each data word is, because now the data words are just full of zeros. So like over here you have a synchronization bit here, and then a bunch of zeros, that's a data word. And if I start playing something, then you can see that suddenly these ones are starting to appear in the data area. So the next signal in the headphones output path is I2S, and I2S is used elsewhere on the board for the 2 auxiliary inputs. So the 2 analog inputs, they run I2S. In this case, I2S is running on a very short distance. There are no test points, so I had to break out these fancy cheap hooks, because like this is so fine pitch that even the regular easy hooks from the logic analyzer were actually too big, so I have it connected in like 2 steps. And despite the name I2S, it's not related to I2C, it's more like an SPI with an extra control signal. So let's go to the oscilloscope and take a closer look at these. This is the logic analyzer connected to the board. Like, yeah, this oscilloscope is a mixed signal oscilloscope, so it's got a 16-channel logic analyzer built in. And on the bottom, these 3 signals are I2S, and on the top one, labeled D3, is the SPDIF signal. As you can see, they are perfectly synchronized. And I2S is a 3-wire bus. You've got 2 clock signals, D1 and D0, and a data signal. So if I like pause the signal from the computer, you can see that the data signal is going silent. The SPDIF is basically all zeros, as you could recall from the previous clip about Manchester coding. So you get only sync words and maybe occasional blips of data. And I2S uses 2 different clocks. So the bottom one is a sample clock, which corresponds to single bits in the data line over here on top, And then additionally you have a left-right clock which alternates every 16 samples and indicates whether the current sample being transmitted is for the left or the right channel. So I2S by default sort of transmits 2 channels for stereo sound. And pretty much the rest of it is SPI. Basically, if you take a closer look, here, you've got your sample clock down here, and then the data is being simply clocked by the sample clock, and the left and right channel alternates every other sample. In I2S, these signals are generally called SCLK or OSCLK. So S stands for sample, so that's the SCLK sample clock. Then you've got the left-right clock over here, that's the LRCK. And the data is just called data or S data, that's the top one. And yeah, as I said, you can see that they are perfectly synchronized with the SPDIF signal. So if you take a closer look at the left and right clock, you can see that the transitions of the left and right clock fall exactly between the SPDIF transmitted samples. This is actually such a nice image that I'm gonna take a screenshot of it. And so we have arrived to the actual analog output. So I've turned channel 1 back on and I'm sampling the analog output from the DAC. So this is like one of the signals for the right channel. As I said, this is a stereo differential DAC, so it creates 4 analog signals, and then these signals are simply fed to the analog frontend, which drives the headphones. And as you can see, the frequency of the audio signal is quite low compared to the frequency of the sample clock. So if I zoom in, you can, the speed the scope's actually switching to equivalent time sampling mode, so we get to run it a bit slower a lot. You can see there is a bit of crosstalk and to some extent like a staircase shaped signal. So yeah, you can see how the DAC actually forms the signal, but this doesn't mean that the actual signal is on the output and headphones output is staircase shaped, because it has to be run through a low-pass anti-aliasing filter as part of the anti-aliasing and digital to analog conversion. So there is one more measurement that I would like to do on this thing, because when I was playing with it, I've noticed that it's extremely loud, to the extent that just a normally fed signal to my 600 ohm headphones, they would be already too loud to listen to at the volume knob set at about 1/3 of the range. So I'm just curious how many dBUs this thing can put out. So a dBU is an unloaded decibel, where 0 dBU is 0.77 volts RMS into no load. So yeah, the scope's got a input impedance of about 1 meg, and this is even a 10x probe, so it's 10 meg ohms. We can easily call this unloaded. I've got Audacity open here, and I have generated a 1 kHz square wave of with amplitude of 1. And if I play this, take a look at the scope. When I start increasing the volume, you can see the sine wave starts to appear. Let's maybe lock the trigger on this, and I can go higher and higher, and I need to measure the RMS voltage, and we're getting 1.97 volts RMS. So as you can see, this thing can output about 8.1 dBu, which for a 600 ohm load is the same in dBm. So that's the maximum output power of that driver. So that's per one channel, 6 milliwatts.